Section 8.1, arc length. How to find the length of an arc. This reminds me of the area under the curve, something like this. If you want to find the area under this curve, this is not a square, not a circle, not a rectangle. So that's where calculus kicks in to help us find the exact area below the curve. Now the same thing, if you are given an arc like this is arc or curve. How do I find the length of the arc from A to B to get the exact arc? So what mathematicians did, they said, okay, I can, same concept in the area when they did rectangles, and then from there, you know, they tried to have more and more and more rectangles. So they said, okay, I'm going to pick several points on the curve like that, and then, you know, connect this to this, all these points, join them together, and then they use the distance formula to find, you know, the length of each piece. But those pieces, you can see them now because they are very like visible to us now. But in reality, what they did, so this, if you add all the sum of these distances in orange together, if you add them up, that will give you the approximate length of the arc, but not the exact, right? Not the exact. So then mathematicians start saying, okay, I'm going to make it smaller and smaller, those pieces in orange. I want to make them small. The smaller you make them, the closer the total pieces added to the actual length of the curve. Make sense? So then that's where I'm going to show you. So recall the distance formula is this. If you remember, x2 minus x1 squared between 2 points plus y2 minus y1 squared. So they use this formula as a distance formula, and they come up with the length of an arc. They said, as a theorem, we say if f prime is continuous, if f prime is continuous on the closed interval AB, then the length of the arc or curve defined by y equals f of x over the interval from A to B is given by L equals the integral A to B, the square root of 1 plus f prime of x all square dx. So you can tell if you look at this, the square root 1 plus something something. So originally it was not like this. It was something square plus something, but then they did the factoring and pulled the thing out, which I'm not going to prove it now. And then what they did, they added up all the sum of these pieces. That's what the integral came from A to B. That's what it is. You might find people write it in a different way, like A to B is still the same, but they write, instead of writing f prime of x, f prime, they write dy dx squared and then dx outside. This is called Leibniz notation. Leibniz notation. So if you see the first one or the second one, or use either one, is totally fine. Now this is if the graph or the function or the curve is written as y equals f of x. But if the function is given in the form x equal instead of y equal g of y, where y from C to D, then the length of the arc, length of an arc from C to D is given by the integral C to D, the square root of 1 plus g prime of y square dy. Or we can use Leibniz notation, or with Leibniz notation, C to D, the square root of 1 plus, here it's not dy dx, it's dx dy square dy. Now one thing, an example, and that will help us to see where the formula is coming from, is how do we prove the distance formula using calculus? Okay, we show how the distance formula came from using the Pythagorean theorem in the xy plane, but we actually can use calculus to prove the distance formula, and that's what we're going to see now. So let's look at this example. Find the length of the curve from the point x1, y1 to the point x2, y2 on the graph of y equals f of x mx plus b. See, this is a straight line, so you expect that we end up with the distance formula because you have 2 points x1, y1, x2, y2. So we have f of x, again, it's mx plus b. In the formula, I need to know the derivative of the function, which is m. So I could use it when I want to find the length. So when I'm finding the length of this, remember the formula said a to b, the square root of 1 plus the derivative of the function. You square it, don't forget to square it, dx. And if you draw like an x-axis like this, see, we're going from here to here, from x1 to x2. Make sense? X equal x1 to x2. So the length would be the integral from x1 to x2, the square root of 1 plus. We found the derivative for that one. But we're not going to just put m. We define m as a slope, y2 minus y1 over x2 minus x1. So we're going to put that in here, y2 minus y1 over x2 minus x1, all squared dx. Then we're going to do some work inside this to be able to integrate it. So x1 here, x2 there. What I'm going to do is I'm going to split this y2 minus y1 square and make it x2 minus x1 square dx. So I rewrote it this way. And why did we do so? Because that will help me to combine the fractions, combine the two fractions together. x2 minus x1 square plus y2 minus y1 square all over x2 minus x1 squared dx. And guess what? So all this radical term is all constant because x1, x2, y1, y2 are constant. So when I'm integrating this function, all I have to do is just pull that out as maybe x2 minus x1 square plus y2 minus y1 square over the denominator is x2 minus x1. Okay, the integral of that is x. So it goes from x1 to x2. So then keep this the same, x2 minus x1 square, y2 minus y1 square. Keep the denominator the same. And that x, you can substitute the upper bound minus the lower bound. These cancel each other, and that will give us the square root of x2 minus x1 square plus y2 minus y1 square. Let's look at a different example. So they ask us find the arc length find the arc length of the curve defined by y equals f of x equals x cubed over 6 plus 1 over 2x on the interval 1/2 to 2. So the first thing I always do is find the derivative for the function. So f prime of x, keep the 1/6 out, 3x squared, keep the 1/2 out. You can write that as x to the negative 1 becomes negative 1, x to the negative 2, which can be simplified to 1/2 x squared minus 1 over 2x squared. If you like to combine them, you're welcome to do so. As 2x squared goes here, you get x to the 4th minus 1. That's f prime of x. Now, we write L, the integral from 1/2 to 2, if they are given, the square root of 1 plus that derivative that I found, square dx. Now the quantity under the square root is not constant anymore. What we're going to do with this is we are going to, the smart way around this is squaring on the top, 4x to the 4th dx. And then we are going to combine the fractions. 1/2 to 2. We get 4x to the 4th. And we need to expand that one, x to the 8th minus 2x to the 4th plus 1 using a minus b squared formula. So for this one, it becomes equal to 1/2, 2. On the top, I can do square root on the top, which is x to the 8th plus 2x to the 4th plus 1 over the square root of the bottom one, dx. Then I can, on the top, do a perfect square, rewrite as x to the 4th plus 1, so I could take it outside the square root. So the one on the top is x to the 4th plus 1. The one on the bottom is 2x squared dx. Now it becomes easier to integrate, especially no square roots. So to do this, we can split this into two fractions. First one would go x to the 4th over 2x squared, 1 over 2x squared dx. This becomes 1/2 x squared, 1/2 x to the negative 2 dx. this one integrates as x to the third over 3, 1/2 x to the negative 1 over negative 1 from 1/2 to 2. This is x to the third over 6 minus 1/2 over x from 1/2 to 2. So you substitute the 2 first, and then you substitute the 1/2 next, and then get the answer, which should be 33 over 16. Next example, we're going to do the same thing. Find the arc length of the curve defined by y minus 1 cubed equals x squared over or on the interval 0 to 8. 0 to 8. We're going to solve for x. So x squared is y minus 1 cubed. So x is, plus or minus the square root of that, which you can rewrite it as y minus 1 to the 3/2. Then we need to find the derivative for that. So that's called g of y, g prime of y, or dx dy, plus or minus, you bring the 3/2 down, subtract 1 from the top. Then we're going to go to the integral. We're going to go to the integral. So the length of the arc is going to be the integral from a to b is given over the y value 0 to 8. The square root of 1 plus that derivative that we found, square, don't forget the squaring, dy. So we're going to change, can we make a slight change over the bound 1 to 8? 1 to 8. And now when we integrate this, so now this 1 to 8 square root of 1 plus, this becomes 9 over 4, and the square will take care of the 1/2. Again, 1 to 8 square root of 1 plus 9 over 4y minus 9 over 4 dy. 1 to 8, the square root of 9 over 4y. If we combine these, we get negative 5 over 4, which you can rewrite it as 9y minus 5 over 4 dy. And that 1/4, you bring it outside as 1/2. It becomes simply 9y minus 5. And then what we can do, we can use the u sub, u equals 9y minus 5, dy is 9 dy. You can multiply in and out by 9 and 1/9 outside. That would give us 1 over 18, the square root of 1 to 8. We need a 9. And then I'm assuming everyone can finish this. The answer will be 67, square root of 67 minus 8 divided by 27. Now we look at one other example. Same thing, find the arc length for this curve, natural log of cosine x from x equals 0 to x equals pi over 4. So again, we have y equals natural log of cosine x from x equals 0 to pi over 4. We found y prime, which is negative sine x over cosine. That's negative tangent. Recall the derivative formula for natural log of u. It's u prime over u. From here, we can write this as 1 plus tangent square x dx So 1 plus tangent square is what? Secant square, which can be rewritten out as secant x dx. And we learned from before a formula for that. Natural log of the opposite value of secant x plus tan x from 0 to pi over 4. The rest is substitution now. Natural log of secant pi over 4 plus tan pi over 4 minus natural log of secant 0 plus tan 0. Secant pi over 4 is the reciprocal of cosine. That would be square root of 2. Tangent pi over 4 is 1. Secant 0, so it's like 1 over cosine 0, which is 1. And tan 0 is 0. So we do natural log, keep this the same, no need for opposite value because that's always positive. And the last one is natural log of 1, which is 0.